नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आप सभी का स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर आईटी जेईई एंड नीट। और मेरी आप सब लोगों से रिक्वेस्ट है कि इफ इट इज पॉसिबल यू शेयर दिस वीडियो ऑन योर सोशल मीडिया लाइक ट्विटर एंड फेसबुक सो दैट इट कैन रीच अप टू maximum number of needy students. Let us start our video. So this is episode 23 of JEE Advanced Problem Series, and this is a thermodynamics challenging problem from adiabatic process. मैं आपसे रिक्वेस्ट करता हूँ कि आप एक बार कॉपी पेन निकाल लें और इस प्रॉब्लम को ट्राई करें and see that how many of you are able to crack this problem. So first I am reading the problem, and then after reading the problem you can pause the video and you can try by yourself. So a heat conducting piston can freely move inside a closed thermally insulated cylinder with an ideal gas. In equilibrium, the piston divides the cylinder into two equal parts, the gas temperature being equal to T naught. The piston is slowly displaced. Find the gas temperature as a function of ratio eta of the volumes of greater and smaller section. Let us start solving this problem. So what I got from this is the whole cylinder is conducting, and inside the cylinder there is a piston. This piston can freely move, and this piston is conducting. The whole container is non-conducting, but piston is conducting, means heat energy can flow from left hand side to right hand side and vice versa. So initially, whatever the given condition is, I can say that if T naught is the initial temperature on the left hand side, then T naught is the temperature on right hand side, because they are saying that the system is in equilibrium. In equilibrium, the piston divide the cylinder into two equal parts. So if I take the volume of the left hand side is V naught, on the right hand side also the volume will be V naught. This can freely move, and in equilibrium condition, the pressure on the left hand side is equal to the pressure on the right hand side. So I can take that the pressure on the left hand side is P naught. On the right hand side, the pressure is also P naught. If the pressure, volume, temperature on the left hand side and right hand side will be equal, it means that the number of moles of the gas on the left hand side and right hand side will be same. So during this whole process, we can say that there is no exchange of heat energy between system and surrounding. So for the whole process, we can say that the change in internal energy of the whole system is equal to the exchange of work energy between system and surrounding. Change in internal energy is equal to exchange of work energy between system and surrounding. So if we talk about the left hand side is not participating in adiabatic process. The right hand side is not participating in the adiabatic process, but the whole system is participating in adiabatic process. So the first thing is when we are moving this piston slowly, slowly means this process should be reversible. So it is an, I'm talking about the whole system. The whole system is participating in adiabatic reversible process because the piston is moving slowly. So we'll say that this is expanded reversibly and this is compressed reversibly. And when we are talking about reversible process, this piston is moving very slowly. So we can say that the pressure on the left hand side and the right hand side of the piston is almost equal. So during the process, the pressure on the left and right is almost equal, right? They may change, but the pressure value is same on the left and right hand side approximately, because in reversible process, we can say that the driving force and opposing force is almost equal. So the whole volume of the system will remain constant. Suppose if I am saying that the volume of the smaller section now is equal to V, then the volume of the larger section is equal to eta times of V. So here it is mentioned that find the gas temperature as a function of ratio eta of the volumes of the greater and smaller section. So I can calculate that what is the volume of smaller section and volume of greater section in terms of V naught, because the volume is conserved. So we can write here that 2 times of V naught, this is the total volume of the system, is equal to eta into V plus V. So from here we get the value of V. V is equal to volume of the smaller section is equal to 2 times of V naught upon eta plus 1. And if we know the volume of the smaller section, we know what is the volume of greater section, which is equal to eta into V. So that can be written as 2 times of eta into V naught divided by eta plus 1. So now we know that what is the volume of the right hand side section and the left hand side section. Since we know that for overall process net change in internal energy is equal to work done. So let us try to write, because the number of moles on the left hand side and the right hand side of the gas will be same. राइट मोल्स हमने अभी निकाले कि क्योंकि ये इक्वल वॉल्यूम है, इक्वल प्रेशर है, इक्वल टेम्परेचर है, तो मोल्स लेफ्ट एंड राइट हैंड साइड में सेम होंगे. And the left hand side is participating in reversible expansion, while the right hand side section is participating in reversible compression. तो पूरे प्रोसेस में अगर देखा जाए तो सिंस वी आर मूविंग द पिस्टन, अपने आप तो ये मूव नहीं कर रहा है क्योंकि अपने आप इक्विलिब्रियम कंडीशन में था, तो somebody from outside the system is moving this piston. So energy is coming from outside into the system in the form of work, right? So if the energy is coming into system, the internal energy of the system is going to increase. That is fixed, that internal energy of the system in this process is going to increase because energy is coming from outside. So this is important that कि जैसे ही हम यहाँ पे इस पिस्टन को धीरे धीरे मूव करेंगे, क्योंकि हम इसको रिवर्सिबली मूव कर रहे हैं और ये पिस्टन कंडक्टिंग है, तो अगर टेम्परेचर चेंज होगा तो टेम्परेचर जल्दी से इक्विलिब्रियम स्टेट में आ जाएगा, क्योंकि वी आर डूइंग इट वेरी स्लोली. सो व्हेन वी आर मूविंग इट स्लोली, सपोज हियर energy is entering into the system, so internal energy of ideal gas will going to increase. So internal energy of ideal gas is going to increase means the temperature of ideal gas is going to increase because change in internal energy is ncv dt. अगर यहाँ का टेम्परेचर चेंज होगा एंड दिस पिस्टन इज कंडक्टिंग, यहाँ का टेम्परेचर भी चेंज होगा, तो हम ये कह सकते हैं कि ड्यूरिंग द प्रोसेस द टेम्परेचर ऑफ लेफ्ट हैंड साइड एंड राइट हैंड साइड बोथ आर चेंजिंग, बट बोथ हैव द सेम टेम्परेचर बिकॉज ऑफ दिस कंडक्टिंग पिस्टन. तो पूरे प्रोसेस के लिए अगर मैं फर्स्ट लॉ लिखता हूँ, राइट, सो फॉर अ स्मॉल स्टेप आई एम राइटिंग दिस, फॉर स्मॉल स्टेप I can write that the net change in internal energy, that is internal energy on the left hand side, इसको मैं delta U1 कह लेता हूँ, plus internal energy of the gas in the right hand side section, that is du2, should be equal to the exchange of work energy in the left hand side section plus exchange of work energy on the right hand side section. So for the left hand side section, in both sections, the number of moles of the gas are equal, right? तो मैं यहाँ लिख सकता हूँ, this is, and gas is also same. So N into CV, CV in the left and right is same because the gas is same into dt, right? Because initial temperature of both are same. And during this process, since this process is happening very slowly and this is conducting, so there is an equilibrium of temperature on both sides, right? So that's why I'm writing that the temperature change on both sides of the section will be same. So ncv dt and ncv dt, this is the net internal energy change, which can be written as the work done in section 1, right? लेफ्ट हैंड साइड यहाँ एक्सपेंशन हो रहा है, लेकिन वर्क डन का जो फॉर्मूला हम लिखेंगे, क्योंकि प्रोसेस रिवर्सिबल है, पी एक्सटर्नल की जगह हम पी सिस्टम लिख सकते हैं. सो वी कैन राइट हियर दैट दिस इज प्रेशर ऑफ द सिस्टम इनटू डीवी. और राइट हैंड साइड वाले सेक्शन में भी ऐसा ही फॉर्मूला लगा सकते हैं, प्रेशर इनटू डीवी, राइट? सो दिस इज द नेट वर्क डन ड्यूरिंग दिस प्रोसेस. तो ये वर्क डन जो है, क्योंकि बाहर से एनर्जी आ रही है, तो ये पूरा जो नेट वर्क डन होगा, दिस शुड बी पॉजिटिव. दैट्स व्हाई इंटरनल एनर्जी इज गोइंग टू इंक्रीज. तो राइट हैंड साइड भी पॉजिटिव होना चाहिए और लेफ्ट हैंड साइड भी पॉजिटिव होगा, राइट? So since if I simplify this ncv dt, I can write this as 2 times of n into cv into dt. और राइट हैंड साइड में अगर मैं लिखता हूं तो प्रेशर इज इक्वल टू nRT, I'm using ideal gas equation. So P is equal to nRT by V into dV, right? And here also I can write that this is equal to, pressure की जगह मैं लिख सकता हूँ nRT upon V into dV. So this n is going to cancel out on the left hand side and right hand side. So we can cancel out the value of n. And CV we can take on the right hand side. So now if I write this is equal to 2 times of dt, टेम्परेचर यहां से हम लेफ्ट हैंड साइड में लेके आ सकते हैं, दैट इज इक्वल टू R अपॉन CV, माइनस साइन इज देयर, dV अपॉन V माइनस R अपॉन CV, dV अपॉन V. So I cannot add these two because यहाँ पे वॉल्यूम जो फाइनल है वो सेम नहीं है. So that's why I'm not adding here. The change in temperature is same in both sides. That's why I have added. But here I cannot add it. So now if I integrate both sides, I can write that initial temperature is T naught and final temperature is same, right? So that's why T I have to calculate. This is minus RCV. It will be outside integration. Initial volume of the left hand side is V naught and final volume is eta times of V. Similarly, here the initial volume of the right hand side section is equal to V naught and the final volume is V, and we know that what is the value of V and eta times of V, we have calculated it. तो अगर मैं अब इसको सिंप्लीफाई करता हूं, इफ आई इंटीग्रेट इट, लेफ्ट हैंड साइड में मैं लिख सकता हूं 2 times of ln T upon T naught, right? So after integration I can write that the left hand side is equal to 2 times of ln T upon T naught, और right hand side में I can write minus R upon CV ln V final upon V initial. I should write eta times of V upon V naught. That is better way to write. So this is the volume, final volume on the left hand side upon initial volume with minus sign is there. Minus R upon CV. If I integrate, I will get this as ln final volume of the right hand side is V. This is eta times of V. Initially it was V naught and V naught. So based on that we are writing here. Now we can put the value. We know that the final volume V is equal to 2 times of V naught divided by eta plus 1, and eta into V is 2 into eta V naught divided by eta plus 1. So from here I can write that V upon V naught, this V upon V naught is equal to 2 upon eta plus 1. And from here eta V upon V naught is equal to 2 eta upon eta plus 1. So now these values we can enter here. So from here I can write that 2 times of, ये 2 को भी हम इस side ले जा सकते हैं if we want, right? So I can write that this is ln T upon T naught and this is minus R upon 2 times of CV. This value is, from here I can put that this value is equal to 2 eta upon eta plus 1. And this value is minus R upon 2 times of CV ln 2 upon eta plus 1. So now if I further simplify this, ये minus अगर मैं अंदर ले जाऊंगा and if I take R upon 2 CV, if I take R upon 2 CV common, I can put this minus inside this log and I can simplify it. This will be eta plus 1 by 2 eta into eta plus 1 by 2, right? So if I simplify this, I can further write that what is the final temperature. So T upon T naught, if I take anti-log and if I put this on the power, so now I can finally write that ln T upon T naught is equal to ln, you can check here that eta plus 1 whole square हो जाएगा ये. So this is eta plus 1 whole square and in the denominator it will be 4 times of eta to the power r upon 2 times of Cv. So you can check here, r upon 2 times of Cv will be in the power, and this is eta plus 1 whole square, and this will be 4 times of eta, right? And for an ideal gas, we can write that Cp minus Cv is equal to R. So if I write that, what is the value of R upon Cv? R upon Cv for an ideal gas is equal to gamma minus 1. So I can also write it as ln eta plus 1 whole square upon 4 times of eta, and this is gamma minus 1 divided by 2. R upon Cv is gamma minus 1, gamma minus 1 divided by 2. If I take anti-log on both sides, I can write that final temperature upon initial temperature. Since for both the sides, both sections, the final temperature and initial temperature is same, is equal to eta plus 1 whole square upon 4 times of eta to the power gamma minus 1 divided by 2. And from here we can write that what is the final temperature? Final temperature is equal to T naught eta plus 1 whole square upon 4 times of eta to the power gamma minus 1 divided by 2. So this is the final answer. This is the final temperature as a function of ratio of volume, that is in terms of eta we have written it, right? So about this problem, many questions can be framed. Can you say that if this is for the whole system I am talking, this is adiabatic reversible process, can you calculate what is the entropy change on the left hand side, what is the entropy change on the right hand side, what is the entropy change of overall process, what is the entropy change of surrounding, what is the entropy change of universe? So I think that in the next problem series, I am going to discuss about the entropy change during the process. So hope that this problem is useful to you. If you are liking such type of problems, to get more such problems, please like and subscribe our channel. Don't forget to share about our channel in your circle. Thank you very much. Bye bye.